What if only a third of added nitrogen fertiliser was ending up in our crop? Where does the rest go? New insights are being gained from a collaborative 3-year research project called Action on the Ground, Reducing On-Farm Nitrous Oxide Emissions Through Improved Nitrogen Use Efficiency in Grains. With a cooperation of 7 farming families and 3 catchment management authorities, Agriculture Victoria research scientists established 9 trial sites within low, medium, high rainfall and irrigated cropping zones across Victoria. 3 nitrogen treatments were applied at each site, based on industry standard practice relevant to each region and the seasonal conditions. Sites received a small rate of nitrogen fertiliser across all plots at sowing, with 0 to 20 kilograms of nitrogen per hectare, typically in the form of MAP or DAP, depending on farmer management. Treatments included Plot 1, a standard practice with urea fertiliser top-dressed at mid-tillering. Plot 2, where urea was applied at double the standard practice, and Plot 3, a control which received no additional nitrogen during the season. Data collected at each site included recent land use history, soil testing, both pre and post-harvest to a depth of 1.2 metres, measurement of nitrous oxide emissions and soil samples at key times during the growing season. Recovery of nitrogen applied as urea fertiliser by the crop, as well as residue nitrogen in the soil post-harvest, and crop measurements including establishment, biomass at flowering, grain yield at maturity, nitrogen uptake and key grain quality indicators. Building on previous Victorian studies, Agriculture Victoria research scientist and project leader Professor Roger Armstrong explains some of the key project findings.
A real standout in our project results was the general lack of nitrogen fertiliser response. This was a function of both the poor seasonal conditions and also the large background levels of mineral nitrogen that we had found. Reducing current rates of fertiliser nitrogen input, particularly in some irrigated cropping areas and also in the high rainfall zone where paddocks have experienced a long history of legume pastures, can have minimal impacts on productivity while saving growers money. As part of his role in the project, Agriculture Victoria research scientist Ash Wallace found that the amount of fertiliser nitrogen used by the target crops ranged from less than 5% to a maximum of more than 60% of the nitrogen applied. This big variation mainly reflected differences in growing season rainfall and irrigation. Average recovery of fertiliser nitrogen by the crop ranged from a high of 42% in irrigated crops to 32% in low and medium rainfall dryland systems to a low of 30% in the high rainfall systems. These values are considerably lower than the figure of 50% currently used as a rule of thumb by many in the industry. Of real concern to growers is the large losses of nitrogen fertiliser that we have recorded. Fertiliser nitrogen recovery in the crop, plus that remaining in the soil at harvest, averaged only 71%. It varied from 63% in the high rainfall zone to 76% in the low medium rainfall regions. This represented an average loss to the crop source system of over a quarter of the fertiliser nitrogen applied. In-crop mineralisation, where mineral nitrogen is produced from organic nitrogen in the soil, was found to be a potential major source of nitrogen to the crops in this study, constituting up to 63% of the total nitrogen in the crop. The relative importance of this source of nitrogen to crop nitrogen uptake appeared to vary predominantly with in-season rainfall rather than soil type or region. Currently, in-crop nitrogen mineralisation isn't very accurately accounted for in best management practices, so it's really important that it is if we'd have accurate nitrogen fertiliser predictions. The best strategy to reduce both costs and nitrous oxide emissions in these systems appeared to be through increased crop utilisation of soil nitrogen, i.e. soaking up excessive nitrogen and reducing fertiliser inputs accordingly. Findings from similar trials in the high rainfall zone also indicate that avoiding nitrogen application at sowing, if pre-sowing assessments of soil mineral nitrogen levels show high background levels of N, and delaying fertiliser applications until between tillering and early booting growth stages improves both nitrogen utilisation and increases crop yield and grain protein levels. A key output of the project will be the development of both localised crop utilisation coefficients as well as a methodology for predicting in-crop N mineralisation. Having both of these tools will help growers and advisors better predict how much fertiliser nitrogen is required, as well as having greater confidence in their decision-making process. The most important practice that growers can adopt is to measure the amount of mineral nitrogen in the profile prior to sowing using deep soil testing. Research undertaken by PhD student Catherine Dunsford in the project assessed new soil testing methods for measuring potential rates of nitrogen mineralisation. Both the hot KCl and Savata tests perform better than current rules of thumb, which are widely used by advisors. These tests look promising for rapid in-field use by croppers once they've been calibrated for southern Australian conditions. Another key finding from this study was around nitrous oxide emissions. High nitrous oxide losses were recorded from the high rainfall zone sites, which appeared to be underpinned by high soil carbon and nitrogen levels. However, the real surprise was that the highest nitrous oxide emissions occurred in irrigated cropping paddocks of north-central Victoria. These emissions seem to be underpinned more by irrigation and poor drainage than by soil carbon and nitrogen levels, which were relatively low at these sites. Very low levels of emissions were recorded in the low and medium rainfall cropping sites.
So, what did farmers involved in the trial think about the findings?
I got a lot of information out of the findings. I have been informed that the losses from nitrogen applications of a high percentage, but in our area we're not losing a lot. During the dry years, a lot was going into the soil and staying there for the following year, whereas we were thinking we were losing it and having to apply more. So now I can reduce the amount of nitrogen I'm applying, knowing that there's backup in the soil for the following year. Deep soil testing is important. In the past we were believing we were losing the nitrogen, but now knowing with deep soil testing I can get a knowledge of how much nitrogen is in the soil, so that during the season I can apply the correct amount, so I'm not wasting the amount of nitrogen I'm applying. This knowledge helps me to plan for the season. It reduces our costs, it reduces our effect on the environment, and we get as good, if not better, yields each year. So we win in many ways.
So, in summary, this project indicates that in many cases there's actually sufficient soil nitrogen present in the soil profile prior to sowing to meet most of the crop demand. By undertaking appropriate soil testing, grain growers could save the expense of applying nitrogen fertiliser that the crop simply doesn't need. Losses of fertiliser nitrogen and presumably background soil nitrogen from the soil can be significant, representing both a major financial loss to grain growers and a negative environmental impact from nitrous oxide emissions. For more information about this project and how you can access the results and tools, visit www.agriculture.vic.gov.au or contact one of our team members.